So today we have Gavin Hurd, who will speak about his PhD work on prequantization of gerbs and non-exact Courant algebroids.
Okay, thank you very much. Thanks everyone for coming. So the way I'm, well, first of all, actually, can you hear me all right through the microphone?
They'll complain if they can't.
Okay, they'll complain if they can't. So yeah, the structure is we're going to start with this this non-exact Courant algebroid, and we're going to sort of make some assumptions on this thing and use this to produce a geometrical interpretation, essentially. So I'm going to split this up into 4 sections. So first of all, I'll just talk about the Courant algebroid t plus 1 plus t star. We're going to go through just a description of this thing. We'll talk about its symmetries. Before finally getting to twisted versions. Sorry, versions. So for the next section, we're just going to go through the analogous result to what I want to present in the case of the Courant algebroid on t plus 1. Then we'll do the exact case. And finally, we'll put 2 and 3 together and use this to frequantize t plus 1 plus t star. Okay. So this will be the general structure, and I'll try to have a little break for questions in between each section. So to start, I've told you, well, I've told you this is a Courant algebroid. We're just going to have a smooth manifold M. And we can form this bundle plus 1 plus e star M over M, where this 1 is just a trivial rank 1 bundle over M. And we're adding all of these things up. So this is what I'm just going to call t plus 1 plus t star from now on. So I've told you this is a Courant algebroid, so I should tell you its inner product, its bracket, and its anchor map. So throughout, I'm going to use little x and y to denote sections of this bundle. And so this will consist of a vector field, a function part, and a one-form part. So the inner product of x and y, we just get this by inserting x into, well, and I'll also write y is equal to y plus mu plus eta. So we insert x into eta, we insert y into c, and then we just add the product of the functions. The bracket is a bit longer. So for this, we first of all want to take the bracket of the vector fields, then the Lie derivative of x with respect to eta minus the Lie derivative of y with respect to c. Just going to look at my notes to make sure I don't get any of the terms wrong here. Minus 1/2 of dix eta minus, sorry, I want the d outside, dix eta diy c plus mu d lambda minus lambda d mu. And then finally, plus ix d mu minus iy d lambda. Okay, so this is quite long, but this is the skew version of this bracket. You can see that by interchanging the arguments, you would get the negative of this thing. There's also a Dorfman version of this bracket that is obeys the Jacobi identity but isn't skew, and this one is skew but doesn't obey the Jacobi identity. And finally, we have an anchor map, which is just the projection from t plus 1 plus t star down to t. So this triple is a Courant Algebroid. So these things are studied extensively in the thesis of Roberto Rubio, and that is the reference that I'm using for this entire first section of the talk. In that, he proves that this is a Courant Algebroid both by computing all the axioms by hand, but he also realizes this from a reduction procedure on the standard exact Courant Algebroid of M cross R plus T star of M cross R. But that's not super important for what we're talking about now. So I've thrown around the term exact or non-exact Courant Algebroid a bunch. I should probably say what that means. So if we have a Courant Algebroid E that fits in a short exact sequence like this, we call E an exact Courant Algebroid. I think it's pretty clear just from the structure of t plus 1 plus t star. It's not going to fit in an exact sequence like this, but it does fit in a short exact sequence like this. So for this reason, Rubio calls these things odd exact Courant Algebroids as well, just because it's essentially the simplest possible Courant Algebroid that isn't exact. Okay, so this is the Courant Algebroid structure. Now I want to talk a bit about symmetries, starting with the inner product. So if we look at the infinitesimal orthogonal transformations of the inner product, well, there's an isomorphism from this to wedge 2 of t plus 1 plus t star, which we can expand out. We get the endomorphisms of t, and then wedge 2 t star, its dual, or wedge 2 t, and then just t star and t. So if we're looking at sections of this thing, let's say, we have two types of important elements. In here we have the B fields. These are two forms, right? And these are a standard type of symmetry we see in the exact Courant Algebroid case. And in here we have A fields one forms. These are not seen in the exact case. This is something new. So these can act on sections of the Courant algebroid. B acts on little x by, all it does is contract the vector field part with the two form B to give you a one form. So this is Ix B, and then the A fields act on these generalized vector fields as well. You contract X with A, but you also, so this is a function part, right? Because you're contracting a vector field with a one form. And then you also have a one form part by multiplying the function by A. Okay? So something to notice about these two things is
What is
just acting,
commutation?
neither of them leave oh,
I just can't. What does it say? IXA minus.
oh, sorry, this is minus 2 lambda times A. Is that too low to see, or?
No, it's just that it's the resolution, but it's okay.
Okay. So yeah, you'll notice that if you, yeah, neither of these leave an X part remaining of the section, and this one doesn't leave a function part either. So if you act B on AX, you're just going to get 0. Similarly, if you act A on BX, you're also going to get 0, because neither of them touch the one form part of the section. So these things actually commute. And so it makes sense for us to define, for us to exponentiate this to get something, to get an orthogonal transformation. And we can exponentiate them both at the same time. So I'm going to write these B plus A fields are equal to just the exponential of B plus A, or the exponential of B times the exponential of A, what have you. These are the same thing because of the commutation relation. The last thing to notice here, though, is that these A fields, the action of the A fields doesn't commute with itself. If you have two different A fields acting, you can't commute them. So this lies in SO t plus 1 plus t star, or a section of it, really. But yeah, and this is a non-abelian group. It has the composition law that if you have a B and an A, and you try and compose these two things, B prime, A prime, this is equal to, well, you just add the B's together because they commute with each other. You add the A's together, but you also have this wedge product of the A's interfering with the B component. So yeah, this is a non-abelian group is the point with this composition law, if we look at these elements. So far, I've only told you about the inner product, right? We want to know how these things interact with the bracket as well. So I'm not going to go through the computation fully, but there's a theorem in Rubio's thesis that if you act these on the bracket, acting on an X, take the bracket of the BA acting on a Y, then this is equal to the A plus B field acting on the bracket of X and Y, plus, and again, I'm just going to check my notes to make sure I don't get this wrong. Okay, you hook in the X and Y vector fields to dB plus a wedge dA minus 2 Iy Ix dA times A plus Ix Iy dA plus 2 lambda Iy dA minus mu Ix dA. So this is a really long expression, and all I want you to get out of it is notice how every single one of these terms in the second part of this expression depends on dA or dB. So if A and B are closed, then we have that the BA field is an actual symmetry of the Courant bracket, right? Then BA acting on X, BA acting on Y is just BA acting on the bracket of X and Y. So because of this, we're going to talk about, I was told to just use these two boards, so I think I'm just going to erase this one. The person came in here beforehand and said I should only use these two.
It's for the recording. I can move the camera.
Okay, let's just move the camera then. Okay, so yeah, we're going to define this new set of 2+1 forms that are closed. This is just the A plus B fields in sections of SO T+1 plus T star so that B and A are closed. Okay, so yeah, so there's a, and then yeah, Rubio has a theorem that if you take the symmetries of M, so the diffeomorphisms of M, can semi-direct product this with these 2+1 closed forms, and this is all bracket preserving orthogonal transformations. So, well, we're not really super interested in the symmetries of M itself. So these 2+1 forms are what we're going to be focusing on. So now that we have the symmetries of this T+1 plus T star, we can talk about twisted versions. So if I have an open cover of M UI, I can look at this bundle over each UI. TUI plus 1 plus T star UI over UI. Similarly, I can look at the same thing over UJ. And I can map between these using a 2+1 closed form on the double overlap Uij. Right? So this will be Bij, Aij, where Bij, Aij is in omega 2+1 Cl Uij. So this will map these. We can use this to glue these together in a way that respects both the inner product and the bracket structure. But it's not enough to just have these things on the double overlaps. We also want to know that if we map to the bundle over UK over UK, this should be the same as mapping just directly from UI to UK, right? So gluing from UI to UK should be the same as gluing from UI to UJ and UJ to UK. So from this, we get a co-cycle condition on these 2+1 forms. This should be equal to 0. But the delta here, right, is not the like standard delta that's just addition. It's composition in this group SO of t+1 plus t star. So this actually gives us a pretty big equation in the Bij's and the Aij's. It looks like, so this equation is the same thing as saying Bij, or maybe I'll write it as delta. No, that's confusing. I should write it all out. Bij plus Bjk plus Bki plus Aij wedge Ajk plus Ajk wedge Aki plus Aij wedge Aki is equal to 0. And also just the standard delta of the Aij is equal to 0. Aij plus Ajk plus Aki is equal to 0. So we're going to use these equations, and we're going to extract a 2 form and a 3 form from these. And this 2 form and 3 form will be the twist for our Courant Algebroid. Okay, so well, first of all, we can pretty easily do this one because it just obeys a standard cocycle condition, right? So I'm going to write the Aij as, this is using the check to Durham isomorphism essentially. I'm going to write this as Aj minus Ai. The Aij are closed, so d of Aij, well, this is 0, is d of Aj minus d of Ai. So this means that dAi, these are global, right? Because, so this is just, these are global because if you take the difference on an intersection, it's 0. So these are just some global 2 form restricted to UI. All right. Now we have a bit more work to do for this part, but we can rewrite this equation using this star here. So using star, we get that this becomes, well, I'm just going to write delta standard of Bij plus Ai wedge Aj plus Aj wedge Ak plus Ak wedge Ai is equal to 0. Okay, so now we have that Bij plus AI wedge AJ. This obeys a standard cocycle condition now. I should really be using, this is the delta in SO of T plus T star. I should really be using a different notation for those two. But this is the standard delta of the check complex. And yeah, so now we know that this thing is actually a cocycle. It obeys a true cocycle condition. So we'll write it as the difference between a CJ and a CI. And now we can just apply D to this whole thing. Well, this gives us that dCJ minus dCi is equal to, well, D of Bij was closed to begin with, so it's 0, minus DAI wedge AJ plus AI wedge DAJ. And this just gives us that dCJ minus F wedge AJ is equal to dCi minus F wedge AI. So this is also a global form, right? Because it's equal on AI and AJ. So I'm going to call this H, restricted to UI. Notice that H isn't itself closed, right? Because this thing wasn't closed to begin with. But if we want to look at DH, well, it's just D of this thing, right? Which is the D of the Cij is 0, so it's 0 minus, well, F is closed and Daj is F. So 0 minus F wedge F. So H is a three-form obeying the equation that DH plus F wedge F is equal to 0. And these are the pairs like this, the pair of F and H, these are the twists for Courant algebroids like this. And I'll go way back to the beginning and just write out the twisted Courant bracket. And that will be it for this section. So the Courant bracket of X and Y twisted by the pair FH is equal to just the regular Courant bracket plus IX, IY applied to H plus F. And then just make sure I get this right. Oh, right, just plus 2 mu IXF minus lambda IYF. Okay. So this is the end of the first section. These are the T plus T star with this new bracket. These are the twisted versions of, T plus 1 plus T star with this bracket are the twisted versions of this Courant algebroid. Any questions? No? Okay, cool. Because of the,
Because this, I don't know, there's what F wedge F.
I see what you're saying, but I don't know the answer. Okay. So, anybody else? Pardon?
If I smell it, actually, then because this F clearly looks like a curvature, and then there's this F wedge F that. Yeah.
Good eye about the F looking like a curvature too. That is what it is. Okay. So yeah, we're now going to do some simpler cases to build up to solving the final problem. And in particular, this first case is pretty much exactly the observation you just made. So on t+1, we have a Courant bracket.
This point, the goal should become crystal clear to everyone in the audience.
Okay.
And so you've defined a structure.
Yes.
That structure is t+1 plus t star on a manifold, but there's a pair F and H of global forms. F is a closed two form and H is a non-closed three form, but which satisfy that equation, dH plus F like F. Right? So you've defined that structure, and the main question is what?
So yeah, we want to make an assumption on this pair of a specific form, and we're going to use these to produce a geometric interpretation of this bracket on M.
Okay, so I would phrase it without that, what do they call it when lawyers use careful language in order to protect themselves from the law? Like, what's the main goal? Forget about making certain assumptions that blah, blah, blah. What's the main
Yeah,
goal?
we're going to use this to produce a principal bundle and a gerb on M.
Okay, that's the answer. So you're saying you're trying to give the answer. The goal is, right, you understand, it's basically the same as his question. His question was, what's going on here? We have a closed two form, which looks like a curvature, and we have a three form, which is not closed, but which satisfies this weird equation. And the main question is, what's going on here? What is the geometric interpretation of this?
Yeah.
Right? That's
Okay.
what it's asking. That's what the point of the talk is, right? So you have to make that crystal clear.
All
You have
right.
to remove all legalese from that question.
Okay.
Otherwise, the point will not get across.
Okay.
Okay.
All right. So we have a Courant bracket on just t+1 that looks something like x plus lambda, y plus mu. This is ix d mu minus iy d lambda. And so this is actually a genuine Lie bracket, but did I write it wrong? I'm not seeing. Oh, right, you are. Yes, good point. Thank you. Yeah, and these are twisted by closed two forms. Is equal to the standard bracket, plus ix, iy, f. So we're going to go through and say what structure does this closed two form F give us? And notice how this is the first part of our like bigger case, because aside from the free form, in our case, we also have this closed two form here. So there's a theorem that if the class of F is in the image of this homomorphism from H2MZ to H2MR, and I probably want to divide this by 2 pi, just induced by inclusion. Then from F, we obtain a principal S1 bundle with connection on M. Okay, so how does this go? Well, let's start with just talking about what this principal S1 bundle is locally, right? So I have the sheaf of U1 valued functions and the check complex here, I, J, U, I, J, K. And to have a principal S1 bundle, I want a function here from Uij into U1, and it has to obey the condition that delta of Gij is equal to 1. So I want something in H1 of this complex. I can extend this complex just by resolving the sheaf U1 a bit. Here I have one forms, and here I have the map d log divided by I. Now something in H1 of this complex, well, you know, H1 occurs here. So I have a one form here, AI. Because I'm just extending the complex by 0, there's no condition on the AI. But if it wants to be in H1, so for Gij AI to be in H1 of this complex, I need to have that delta Gij is equal to 1 and d log of Gij is equal to I delta AI. Right, and this is exactly the condition that the Gij and the AI together are a principal S1 bundle with connection. So, yeah, so these things are elements in H1 of this complex. Now, we can put this complex in a short exact sequence. Well, here I have my U1 goes to omega 1, right? This sits in a short exact sequence like this, right? I can just resolve the sheaf of R-valued functions by differential forms, the standard way. This is a fine resolution. And then I need to be careful with what I add here to make it a short exact sequence, right? I need 0 here, because this is an isomorphism, and I need omega 2 here, because this maps to 0. And so on. So my prequantization condition here is that this lies in the image of this, right? So that's a condition on that sort of exists in H2 of this complex, right? Well, first of all, let's note that, well, so I want you to kind of think of us also having the check derivative direction coming out of the board for each of these, right? So this slice is coming out of the board there. H2 of this middle complex is just the standard real valued cohomology, right? Because this is a fine resolution. If we look at a class in H2 of this, however, it looks a little different. So we have Z, 0, and omega 1, then UI, UIJ, UIJK. So we would have something here, CIJK, and a one form on the on this part. And the prequantization condition that F is in the image of this homomorphism. Well, I'll say something. I'll write this explicitly by saying like CIJK gets mapped to the class of F over 2 pi. So now if I write F here, this maps to 0, and I want to take this class in here and apply the like long exact sequence to it to get a class in H2MR. Okay, so I'm just going to apply the map to get this in H2MR instead. So I'm just going to cross out the coefficients and write the coefficients of this resolution instead. Oh, that was supposed to say omega 2, my mistake. Omega 2. Now, in H2MR, the prequantization condition there is exactly the condition that this is has the same cohomology class as, well, we transport this to be a 2 form. So it's the same cohomology class as the class of F minus 2 pi times the, I should have put a minus there, my mistake. The class of 2 pi F over 2 pi, which is 0. So this is 0 in cohomology, which means that it comes from something. It's D of something in H1 here.
So minus C and F was originally a class in which cohomology?
H2 of this complex.
And what are you doing with that class?
I'm applying this homomorphism to it.
Okay, and what are you obtaining?
0. But then I'm saying, well, it's 0 in cohomology, so it's exact, right? So I've got a real valued function, call this Fij, and a one form AI that maps to this, and I have a 0 along the diagonal, right? So yeah, Fij AI being a primitive for this is exactly the same as it obeying the equations. Here, I'll write them out. Yeah, it's the same as it obeying the equations that delta Fij is equal to minus Cijk. D of Fij is equal to delta of AI. And finally, dAI is equal to F. Okay, but so this is a class in H1 R, or sorry, it's a primitive. It's not a class in H1 MR. It's a primitive for this thing in this part of the complex. So we can apply the homomorphism to it from this complex to that complex, and we'll just get that Fij maps to e to the I Fij, and AI maps to itself. And now if I'm going to call this Gij, if we write these equations in terms of AI and Gij, again, this is exactly the condition that AI and Gij form a principal bundle with connection. Delta of Gij is equal to 1. D log Gij is equal to I delta AI. And the curvature of this connection is what? Well, D of AI is equal to F. So we started with the closed 2 form, and we produced a principal S1 bundle with connection whose curvature is the closed 2 form. Okay. Any questions about this?
Basically, rephrasing of the original argument of constant for prequantization of 2 forms, right? You have 2 form F. Under what condition can you express that F as the curvature connection on a line bundle or on a principal circle bundle?
Yeah. And
it all comes from this short exact sequence of complexes. It's one way of thinking about it.
yeah, and just the last note about this, for the twist on t plus 1 plus t star, we actually did have a closed 2 form, right? So already that the twist produces a principal bundle with connection for us. All right. I'll just continue on here. So in much the same way as we did that, I'm going to go through the prequantization of the exact Courant algebroid now. So yeah, if we look at, so let's be the exact case. So the brackets on t plus t star are twisted by closed 3 forms H. So we're going to make the exact same kind of assumption on H that we made on F before there. We're going to have that if H is in the image of the map from, well, now we're looking at H3 MZ going into H3 MR. I'll have a CIJK L here maps to class of H over 2 pi. Then from H, we obtain an S1 gerb on M with 0 and 1 connection. So I'll just explain briefly what this is, and then we'll go through the result.
To make a irritating complaint. So my irritating complaint is that, okay, so that statement is false. Someone tell me why it's false. Just like the statement that you made about Costant's result, it's false. It's a small, insignificant detail, but it's still false. One. Okay, H is in the image of the map from integer cohomology. And then you say from H, we obtain a gerb. Like out of the 3 forms, you're going to miraculously construct a gerb. Right? Is that really true? Is that really what you intend to say, that out of the 3 form, we obtain the gerb?
I suppose not. It's
That's why you think it's not true. Anyone want to comment on what's going on?
Maybe it's easier to see from here. For example, what happens if that is 0? But if that is 0, then clearly the cohomology class is in the image that you want.
yeah.
So just from knowing that F is 0, can you tell what bundle with connection you get from that thing you want?
I see.
That's not answering it, but it's giving a hint. But if anyone want to just say what the problem is, then you get my support. No, it's not, I'm not quite that pedantic. So let's say that the image in second cohomology, say the 2 form was 0. What kind of principal circle bundle could we get if the 2 form was 0?
The curvature would be 0.
Flat connection.
It has to have a flat connection, but what kind of principal bundle do I get? Does it have to be trivial? Does it have to be a trivial principal bundle?
Okay.
Anyone? Say I tell you that the curvature, I have a principal circle bundle, right? And I tell you that the curvature is just 0, completely 0. What kind of principal circle bundle could it be? Does it have to be trivial?
No.
What could it be otherwise? I mean, if it had a Chern class, which was some class in second cohomology, that class would go into the Durand complex, and I'd get a 2 form, which would be non-trivial in cohomology. So how could I have a non-trivial bundle with trivial curvature? How is it possible? I'm not allowed to say. Shut up. Yeah. It's a Hop. Well, the Hop circle bundle over S2, right? It's S3 over S2. It's a non-trivial circle bundle. That's first term class in H2 of the base. H2 of the base is S2. So H2 is Z. And so you have an integer class, let's say the number 1, which would be this first term class of the Hop bundle. So the first term class is not trivial. The curvature is not trivial. Everything's fine. I'm saying if the curvature is 0, does that mean that the bundle has to be trivial? Okay, please.
Just said that you have a flat number.
Yeah. So
What can
Or torsion.
That, yeah, so the point is that there are torsion classes in the integer cohomology for some spaces. You can have torsion cohomology classes, and those are perfectly admissible as Chern classes. The first Chern class could be torsion. Let's say, what's your favorite example of something that is H2 torsion? So, but the point is that you can't get this S1 bundle only from H. You also need the C. Right? So you're saying if H is in the image from integer cohomology, right?
Right.
There's a choice of lift. You could have several elements C that map to the same H, because you can have torsion in H3 that maps to 0 in the Durand H3, right? So the choice of C is not unique. That's the choice of the bundle. So it's where you get the bundle is the choice of lift of H to C. Okay, so it's not from H that you obtain the S1 bundle, it's the choice of lift to C. You could say that from H comma C, we obtain the S1.
Okay.
Or you can just say there exists a bundle. Good connection.
Right.
But there-
Okay. Yes. Okay.
Okay. Right, let's move. It's just that, you can't stand the idea that the whole room would be thinking. There's no such thing as torsion in H3.
Right. Okay. Okay. So I think I was just going over, yeah, what this means. So a gerb, much like a principal circle bundle, is we have this U1 complex. I'm just going to write it here to start. IJK, UIJK, L. Then we have what we want is a function GIJK that maps UIJK to U1, and we need to have that delta of this GIJK is equal to 1. So this is what a gerb is. We're sort of thinking about this as having a bunch of trivial principal bundles on the UIJs, and then the GIJKs are isomorphisms between, or it's a section of the delta of these principal bundles. And then it has to be trivial on the canonically trivial bundle you get by taking the delta of the principal bundle twice. But this is just a gerb. So we said we wanted a gerb with 0 and 1 connection. So, whoops, I'm going to extend this complex again. Make a 1. Now a class here would be, we'd also have a 1 form, Cij. This is what we would call the 0 connection. If we just truncated it here, we would just have a 0 connection, but I want a 1 connection too. So I'm going to extend this once again, and now something here is also a 1 form Bi. And if I want this to be an actual class, right, then I would need to have that delta of Gij k is equal to 1, d log Gij is equal to delta Cij times I. And finally, dCij is equal to delta Bi. So just to reiterate, this is the gerb, this is the 0 connection, this is the 1 connection. All right, everyone happy with that description? So we're now going to, maybe I'll just go back to this board, because we're now going to put this complex in almost the same short exact sequence here.
Why is there, there's only one there? Is there really like this whole complex? Like, does this go on forever? Like, why do you get to choose the result one by one point there, but one point there?
It depends on the, like I could extend this again, right? And if I put omega 3 here, well, now for this to be closed in this whole complex, I would need that dBi is equal to 0, right? So it's a gerb with flat connection now. So just where you truncate this depends on the object you're going to get. But yeah, I don't want gerbs with flat connection, right? Because I want the curvature of the gerb to be my 3 form that I started with. Okay. So yeah, I'm just going to modify this short exact sequence to be better for our purposes now. I want to go to omega 2 here and then 0, which means I need, sorry, I want to line this up a little better. Omega 2, omega 3. But now this has to be 0, so it's actually a short exact sequence. And, oh, sorry, 0. That's omega 3. That's what I meant.
Put a 0 in there, then you're looking at flat objects.
No, if I put a 0 in there, I'm looking at not flat objects. If I put omega 3 there, I'm looking at.
Thing is that when you draw these diagrams, sorry, this is another irritating, stupid comment, right? When you draw these diagrams, it's like that game that you play when you're a child, like what's missing? What's missing? Right? If there's anything missing, people in the audience are going to be triggered by that. At
Okay.
least I'm triggered by that. Right? So there's 2 things missing. Look at it. There's 2 things missing. If you drew all the arrows going up, but you don't draw some of them,
Oh,
then
yeah.
people wonder why. Why did he do it? And they're going to be transfixed by this question. Why did he write it? So never do that. Don't leave things out, because that's if there's one thing that mathematicians are good at, it is finding little tiny weird errors that are inconsistent. I don't know. Do you agree with this? Did it bother anyone else? Or am I the only one?
I got over it.
You got over it, but it bothered you. Okay, please proceed.
All right. So we're just going to proceed as we did before, right? We've got our complex like this for, well, now we're looking at H3 of these instead. Uij, Uijk, Uijkl. So here we've got our minus Cijkl that we assumed before, and here we've got our 3 form H. That's restricted to UI. So we can map this forward into the R resolution, omega 2, omega 3, and now it's 0 in cohomology because of the condition we've written there. So that means we can find a primitive for this thing, yeah? And that primitive is going to be, well, I'm just going to call it the same thing, a BI there, CIJ there, and a FIJK there. And these obey the appropriate equations. Delta Fijk is minus Cijk L. dFijk is equal to delta Cij, and dCij is delta of the BI. Okay, so, and then finally, we want to map this forward again into, into U1, omega 1, omega 2. And the, these ones are isomorphisms, so the Cij and the Bi stay exactly the same, but the Fij gets mapped to e to the I Fij k, and this equation will be, d log of e to the I Fij k is equal to I times. So now these things define an actual gerb with 0 and 1 connection. All right?
I'm confused about this argument. So here you say you start with data on those two spots, and then you send it forward to the second row of this complex. And then you say, we know that that is 0. How do you know that? Because it seems to me like the argument is really that what's really happening is, I think you can fill that under diagonal with stuff by diagram chasing. And it looks to me like the logic is you can fill that under diagonal. Therefore, the class is 0. Therefore, it's coming from something in H2.
It's 0 because of this assumption. This, like, I could just rephrase this assumption as the assumption that this is 0 in cohomology.
Which complex?
In H3 of R.
Prequantization condition says that global closed form balances out, cancels out with a certain class in Z. Those two classes are in two different cohomologies, but we can put them together in this bottom row.
Yeah.
And it will be a non-trivial class in the third cohomology of that bottom row.
Yes.
The assumption is that when you push it forward to R, it's 0. That's the assumption that the integer class and the Durand class kill each other.
Okay, I think we're saying the same.
Yes, we are. Yes, exactly.
Yeah.
So really what you're saying is that because when you grab this object in that bottom row and you push it up, you get 0. That
Yeah.
means from the long exact sequence that was coming from.
Exactly. Exactly. And I'm calculating what that thing is. Okay.
Okay.
So we're good.
Yeah.
All right. So yeah, that's the end of the third section. For the last section, we're going to put these together to solve the problem for t plus 1 plus t star. Oops. So we're going to need two prequantization assumptions this time. I'm going to make one for the closed two-form F, right? So if you'll remember, our twist consisted of F in omega 2 closed, M, and H in omega 3 of M, not necessarily closed, so that, well, yeah, I don't need to write dF as 0, but I do need that F, wedge F, plus dH, this is 0. Okay, so just focusing in on the F, by the second section of the talk, if we assume that this is in the image of the map from H2 to of H2MZ to H2MR.
What the opportunity have to save a bit of time since you're running low. Let's say we assume F is prequantized.
Right, okay. Assume F is prequantized. and we get a principal bundle P with connection A over M, and dA is pi star F. Okay, so we need like classes to make the prequantization assumption, right? We can't just make it about any form. It has to be closed. And so we can't just directly assume that, you know, H is coming from something, because it doesn't define a class in cohomology at all. But using this A, we do have another class lying around. Namely, we can look at the form A wedge pi star F plus H. Now, D of this, right, that's, well, using that, it's just pi star of F wedge F plus DH, which is 0. So we can make the assumption that this class, A wedge, I'm going to suppress the pullbacks by the projection just to save space, but this is prequantized. So this by itself would give us a principal bundle on M and then a gerb on top of that principal bundle, right? Just by prequantization of a closed 3 form. But we can do better than that, actually. Because now we've got this like extra direction in this complex, right? Before we had the check direction and the sheaf resolution direction, but now we can think of the action groupoid of P as well. So have this 1 cross P S1 squared cross P, etc. So yeah, we're expanding our double complex from before to a triple complex. The issue is, well, we know if we just had a gerb on P, that wouldn't be the right object, because, you know, gerbs on P from the previous result correspond to exact Courant algebroids on P. And similarly, if we look at this action groupoid, we're going to get a like fully equivariant gerb on P, which is also not right, because then it would quotient down to a gerb on M, and, you know, that would correspond to an exact Courant algebroid on M. So what we're actually going to do is take the action groupoid of R cross P over where, yeah, R is just acting on the fiber of the principal bundle P. So now I'm going to revisit this diagram here, but now this is just on the P level, and we have more layers of this diagram coming out of the board, right? So the problem here is that now this class I've written is not closed in this new complex. Because if we look at so yeah, there's another layer above this diagram. It's R, omega 1, omega 2, and then UI, UIJ, UIJK. I forgot to say it here, but this complex has a differential I'm going to call delta R. So yeah, this thing is no longer a primitive for this, because if you if you take d of this in the whole complex, you'll get delta r of those things on the level above, right? So here you would have delta r bi, delta r cij, and delta r of fijk. And for this to be a primitive, we need something here to cancel these out, right? So I'm going to assume I have an fij here, and
What is the complex that you're considering?
pardon, I couldn't understand what was being said.
Sorry, it's just I'm not clear which one of the double complex that you're starting with. Is it the U1 to omega 1 to omega 2, or is it the R to omega, which
It's
one?
the r to omega 1 to omega 2. This is on the, it's a triple complex now, right? Because we've got the action groupoid as well. So this is on the r cross p level of the complex.
But on the just on the P level, it's just the
Yeah.
complex computes the real cohomology.
Yes. This is what the diagram looks like on the p level. Sorry, I'll erase this.
I see.
Okay. So yeah, sorry. Now these things have to obey certain equations to cancel out what we have there, right? We need that delta fij is equal to delta r of fijk. We need d fij minus delta ai is equal to delta r cij. And finally, dai is equal to delta r bi. But we're still not done, right? Because we would need something on the level above now to cancel out we need something to cancel out the delta r of fij and the delta r of a. So r omega 1 there, and then ui uij. And this is on the r cross p level. And I'll say I have a lambda I there, so that delta of lambda I is delta r of fij, and d lambda I is delta r of a. And finally, right, we want this thing to be closed in the delta r direction, so that all of this structure gives an actual class or an actual primitive for that. So we need delta r of lambda I is equal to 0. So this is a lot of equations, but together, what all this means is that from these two prequantization conditions, one on the closed form f on 2, or on m, and then a prequantization condition on this closed form, which is a closed form on p, we get a principal circle bundle with connection on p, and then an R equivariant gerb with connection on top of p. Okay. I think I might stop it there and for questions. And
Do you want to say anything about it? Sorry, stop it in the end.
Well, I do kind of want to talk about like I just don't know if I have time to like get into the like S1 twisted nature of this thing.
So far, what you've explained is that from this pair of forms, you can obtain an R equivariant gerb on a principal bundle you're trying to. By the way, and the gerb has connection, right? It has
Yes,
connection.
our
So there's one last thing that you want to say, so just try to summarize it and be available.
okay. The last thing that I want to say is so on this level we have 1 cross P inside there, right? We could consider pulling all of this structure back to 1 cross P. But on 1 cross P, all of the action is trivial, right? You're just acting by the full circle. So pulling back by the projection or pulling back by the action are the same thing. So all of these equations, the delta R's all go away.
You're talking about the Z inside R.
Yeah.
The integers acting on a full period. So it's kind of like 2 pi times the integers sitting inside R.
Yes. And what you're left with now is, well, oh, my mistake. I forgot to say we should like exponentiate all of the functions to get a gerb instead of just leaving them as these R-valued functions. But once we exponentiate this, e to the I Fij, we're left with what seems to be, sorry, this would be d log e to the I Fij is equal to I delta AI. We're left with what appears to be like a principal bundle, right? We've got function U1 valued functions on the double overlaps that delta to 1 now, and they're compatible with these 1 forms. So at every integer you have that the gerb gives you this principal bundle. So we might say that this is like an S1 gerb, but instead of just getting like a trivial bundle every time you go around, you might have a non-trivial principal bundle that you sort of tensor the gerb by every time you act by going around the circle. Okay. Yeah, I think I'm going to cut myself off there. So yeah, thank you for coming, everyone. Yeah. Anyone have any questions?
Can I ask a question?
Yes.
Just to make sure I understand in summary, the data that prequantizes F and H is 1, a principal S1 bundle, and 2, you form this action groupoid, which is some sort of stack, which is actually, I guess, yeah, it's a stack, and then you have a gerb with 0 and 1 connection on that stack.
Yes. No? What?
I'm not sure why you're trying to avoid like the last part of your talk in which you explained the final piece of information. Right? He said that we just get a principal circle bundle and a gerb on it.
No, a gerb on the stack, right? So it's like a gerb on the total complex of these 2 things, which would be the same as an R equivariant gerb on the principal bundle, right?
Yes, and what you're getting is not it's not an S1 equivariant gerb.
Oh, right, it's R equivariant, but I think
what he's saying is that it's R equivariant.
But if the stack comes from this complex, isn't it?
Isn't the stacking question the original manifold modulo the trivial action of Z? Is that what's happening? Because you have a principal bundle over M, and you're extending the U1 action to an R action. So modding that by R, I would imagine that would be the same thing as taking the original thing and modding by Z.
No, I think this action groupoid is a stack. It's a Z, but you can think of it as like a stack where the fibers are like BZ. So a class in H2 of Z is a Z gerb, and that is like the total space of it. So it's not just Z over M. If that makes sense.
We ran out of time. Let's leave it there. But the point is that what you explained is that it's an article variant gerb which pops out for free another principal bundle. And there's a constraint on what that principal bundle is, which you haven't yet said, which would answer Francis's question.
Oh, I see.
So, okay, well, we have to leave it there, but thank you.